Ferroelectric Random Access Memory (FRAM). Ferroelectric memories use a ferroelectric capacitor where the dielectric material of the typical capacitor is replaced by a ferroelectric material such as Pb, ZRS, Ti1-XO3 and Pb and Sb, Bi2, Ta2O9. Prior to FRAM, magnetic memories using ferromagnetic cores with hysteresis characteristics were developed in 1950s, but those vanished due to large cell area and power consumption. Here you can see the figure hysteresis characteristic of a ferroelectric capacitor QR and minus QR, a red eminent charge QS and minus QS, saturation charge VC, corrosive voltage Vs, saturation voltage CO and C1, linear capacitance for data 0 and 1 respectively. The hysteresis loop of a ferroelectric capacitor is shown in figure. The total charge of a ferroelectric capacitor varies as a function of applied voltage and does not disappear in the absence of electric field QR for data 1 and QR and minus QR for data 0, unlike that of dielectric capacitor. This is because of a spontaneous polarization occurs in the crystal structure of the ferroelectric material. The net change in the direction of the polarization happens when the applied electric field is larger than Vc. No further reorientation can occur after Vs and the polarization is saturated Qs. The structure and the operation of FRAM are similar to those of DRAM except PL, plate line, figure A and B show this core structure and timing diagram to read cell data 1 with the step sensing scheme respectively. Reference cells, which always store only data 0, are placed per column to generate a reference signal used for read operation. Bit lines BL and BLB are pre-charged at VSS since P pre is high. A word line WLO is selected and activated to a boosted voltage VPP for full data restoring in the DRAM. The reference word line connected to the bit line RWL1 is activated at the same time. Step signals are applied to normal and reference plate lines PL and RPL together. The total charge of the ferroelectric capacitor is changed from QR to minus QS, and a positive charge appears on the bit line to maintain charge neutrality. When the word lines are enabled, capacitor dividers are formed by CFN, CBL and CRFN, CBLB, CF, CRF, CBL and CBLB are the capacitors of the normal cell reference cell bit line and bit line bar respectively. Therefore, the resulting voltage here you can see the figures. Memory structure of FRAM: A cell array, B read timing diagram with a step sensing scheme. Reference of data 1 is approximately expressed as delta V1 equal to C1 by C1 plus CBL VDD, where C1 is the linearly modeled capacitance of the ferroelectric capacitor shown in figure. Similarly, the voltage difference of data 0 is expressed as delta V naught is equal to C naught by C naught plus CBL VDD, where C naught is linearly modeled capacitance of the ferroelectric capacitor shown in figure. The capacitance of the reference cell is set to make sure of the voltage signal generated by the reference cell is between delta V0 and delta V1 and is larger than that of the normal cell. After voltage signals are generated on the bit line bar by the normal and the reference cells, the bit line sense amplifier detects and amplifies the signal reference on bitline pairs to VDD and VSS for full data, restoring the total charge changes to QS after the sensing operation and becomes QR after the applied field vanishes. Since the step sensing scheme can cause some reliability issues, a paused sensing scheme also widely used with some read speed penalty, where a pause is applied instead of keeping the voltage at the plate lines. FRAM suffers from two problems inherent to the ferroelectric material, so-called fatigue and imprint. A capacitance charge is gradually graded with the repeated use of capacitance fatigue, and the ferroelectric capacitance tends to stay at one state, preferably over the other, when that state is maintained for long time imprint. Thank you.